Okay, today we're going to go on a little bit in our chapter 4. We've started this with probability and counting rules. We're going to briefly go over what we've done, and then we're going to go on to the multiplication rules, and that's all we're going to cover today. So if you remember, we talked about sample spaces and probability and the addition rules for probability. We're going to go on with the multiplication rules and conditional probability. And then Wednesday we'll do counting rules and the probability and counting rules. So our objective today is we're going to talk about the probability of compound events, number 3 down there, using the multiplication rules, and also the conditional probability of an event. And that pretty much is all we'll cover in this section today. So we went over the definition of probability. I'm going to go through these slides real quickly that we've already gone over. Definition of an outcome, a sample space, and the event. We did some example sample spaces and worked some examples of different types, how you would calculate a sample space. You could make a table. You could just make a list. You could do a tree diagram, something like this. There's lots of different ways to decide how many are in the sample space. There's classical probability, which is successful outcomes over the total number of possible outcomes. Empirical probability, where you do an experiment. And then subjective probability is like the weather. We won't do much with that. So we went over the formulas for these, rounding rules. Just these again are just generic classical probability. Went over the probability rules. These are in your book, so I'm not going to spend a lot of time, and we've already gone over them once. It is important to remember that all the sum of all your probabilities is no greater than 1, and it's always between 0 and 1. It can be 0 and it can be 1, or it could be percentages, 0 and 100%. It's always either a decimal, a fraction, or a percentage. Again, some more examples. We talked about the complement of event, which is, the likelihood that it doesn't happen. Since the total is 1, then 1 minus the likelihood that it happens is the complement that it doesn't happen, or 1 minus the complement will give you the probability of the event itself. Okay, we went over these, and I'm going to go right on through this empirical probability. This is the frequency of the desired class and over the sum of all your frequencies. And we had blood types, classes. Sometimes it's easier to read these from a table, if you remember, than it is to actually count them up. But you can ask a lot of different types of questions. This one, a person has type A or type B, or you could want to know not AB. It could be a lot of different things. Subjective, again, weather forecasting, predicting outcomes of sporting events. So that's what we've already done. We did the addition rules. We talked about events that were mutually exclusive or not mutually exclusive. If they were mutually exclusive, it could be one or the other, but it couldn't. There was no way that it was in both categories that we were looking for. We're looking for 2 different events with these mutually exclusive events, not just one. So if you're getting a 3, getting an odd number. Well, you can get a 3, but a 3 is also an odd number. So it could occur in both categories. And in that case, you have to subtract out one of those probabilities so that it doesn't occur twice. Get that off the screen. There we go. All right, so we're going to go on. And we did all these examples, so I'm not going to go over them again. You should have done homework on this already. Talked about medical staff. Here are the formulas, or here's the multiplication rule. So this is where we're really starting new today. You have 2 events, A and B, that are independent events. And the fact that A occurs does not affect the probability of B occurring. So if it's independent, if there's no one doesn't affect the outcome of the other one, then and you notice the key word there is and. With the addition rules, the key word is or. This happens. In multiplication rules, this and this happens. It's the probability of A happening times the probability that B happens, if they're independent. If they're dependent events, the probability of A and B is the probability of A times the probability of B, given that A has already occurred. That's the way you read this right here, this B slash A that you see right here. Okay, that's B given that A has already occurred. And again, that's dependent events. So let's look at a couple examples. A coin is flipped and a die is rolled. Find the probability of getting a head on the coin and a 4 on the die. Well, if you look here, right here, a head is 1 out of 2. It's either heads or tails, so it's one outcome out of possible 2. On a die, it's 1 out of 6. And so you multiply them, and you can't get any over. There's no way they can both occur. The flipping the coin and rolling the die are two totally separate things. So one doesn't influence the other. So these are independent events. And so that multiply them together and you're going to get 1/12 as your probability that you would flip a head and roll a 4. Okay, another example. A Harris poll found that 46% of Americans say they suffer great stress at least once a week. If, in your case, it's during statistics class. No, I'm just kidding. If 3 people are selected at random, find the probability that all 3 will say that they suffer great stress at least once a week. Okay, so you've got 3 different people that you picked, and it's a 46% chance that they're going to say that they suffer great stress. For each person, it's a 46% chance, or 0.46. So the first person is 0.46. We're basing this on the Harris poll. The second person is 0.46, and the third person is 0.46. And so when you multiply all 3 of those events together, this one, and this one, you get 0.097. So it's not really very likely that all 3 that you pick will say they suffer great stress at least once a week, even though almost half of Americans say they suffer it at least once a week. Okay. Now let's look at another example. At a university in western Pennsylvania, there were 5 burglaries reported in 2003, 16 in 2004, and 32 in 2005. If a researcher wishes to select at random 2 burglaries to further investigate, find the probability that both will have occurred in 2004. Okay, so we want the probability of crime 1 and crime 2. Okay, the probability, and these are both in 2004. So in 2004, if you look up in your data here, there were 16 burglaries in 2004 out of, and you add 32, 16, and 5, the total number that they were looking at over the course of the 3 years. So they're just going to randomly pick some crimes to further investigate. So 32 and 5 is 37, plus 16 is 53. So that's our denominator for the first one. 16 out of 53. Now, these are not independent events because they're both occurred in 2004. So if the second one occurred in 2004, there's now only 15 to choose from in 2004. And instead of 53 events, because we've already chosen a crime to investigate, there's only 52 left out of the total. So you can see that both the numerator here, this 15 is 1 lower because it's the one's already been chosen from 2004, and the 52 is 1 lower because We started with 53 crimes, but we've already picked one, so now there's only 52 left to pick from the second time. All right, so when we multiply those across, we have 60 over 689. If you reduce it if you can, or make it a decimal. Now those are dependent events, and sometimes it's a little tricky to see the difference, but one, you can see that the second outcome is different because we had to take some away. There were fewer choices after choosing the first outcome, the first set of data. So let's look at conditional probability, and that's that B given that A has already occurred. Conditional probability is the probability that the second event B occurs given that the first event A has already occurred. Now, if you rearranged your original formula, see if our original formula before, let's see if I can write on this and it'll show up, was P, let me get my pen here. Okay. All right, I had my original formula that I was looking at was P, A, and B, okay, is equal to probability of A times the probability of B given that A has already occurred. And so what I'm really done here is I've just rearranged this formula to solve for this piece right here. So now I can figure out what the formula is for B given that A has already occurred. Now I want to go back. Well, I'll do another couple examples later. Let's move forward with the PowerPoint. Okay, I have to get rid of this. Yep. How do I get out of this? Okay, I think I'm there. Okay, now another example. The probability that Sam parks in a no parking zone and gets a parking ticket is 0.06. And the probability that Sam cannot find a legal parking space and has to park in the no parking zone is 0.2. On Tuesday, Sam arrives at school and has to park in a no parking zone. Find the probability that he will get a parking ticket. So we have to figure out what's what. We've got, he's parked in a no parking zone, which is the N, and he gets a ticket, which is the T, okay? So the first sentence, the probability that Sam parks in a no parking zone and gets a parking ticket, that's the P in and T. That's the numerator, 0.06. The probability that Sam cannot find a legal parking space and has to park in a no parking zone is 0.2. So that's the probability that he's parked in where he shouldn't be. That's the 0.2. So then the probability that he'll get a ticket given that he parked in a no parking zone is 0.3. It's 0.06 divided by 0.2. So you have to kind of sort out what you're given in the problem. And again, that's sometimes a little tricky, but you've got to look it over and see if you can figure out what you've got. Okay, another example. Women in the military. A recent survey asked 100 people if they thought women in the armed forces should be permitted to participate in combat. The results of the survey are shown. We've got males, yes, no, and a total of 50. Females, yes, no, and a total of 50. So there were 100 people surveyed, okay? So remember that data. Okay, women in the military. Find the probability that the respondent answered yes, given that the respondent was a female. All right, so 8 female respondents answered yes. So yes, given that they're female, is 8. or female and yes, excuse me, is 8. Out of 100, okay? And the probability that they're female, there were 50 females out of 100. And so you divide that, and so it's 8 out of 50, and reduce that to 4 out of 25 is your final answer. Now, you could have shortcut that in a table and seen that we had 8 out of 50 here, 8 out of 50. Okay, but if you just had the words to go by and it wasn't already in a table, you'd do female and yes, there were 8 out of the total 100, and female, there were 50 out of 100. So finding a table many times, or having it in a table, makes the problem a little easier to sort out. Find the probability that the respondent was male, given that the respondent answered no. Well, 18 out of 100 people answered no and were male. Okay. 60 out of 100 answered no. Male and female, 60 of them answered no. So 60 out of 100 said no. So that's 18 over 60. Find the probability the respondent was a male, given that the respondent answered no. That one's a little harder to see, I think, just even from the table. So, but you see hopefully where it came from. 18 answered no and were male. 18 out of the total 100. 60 answered no, so 18 over 60, or 3/10, is what the probability that they answered, that probability that the respondent was a male, given that the respondent answered no. Okay. Neckwear Association of America reported that 3% of ties sold in the United States are bow ties. If 4 customers who purchased a tie are randomly selected, find the probability that at least one purchased a bow tie. Now this is harder with that at least thrown in, because that means that 1 could have purchased a bow tie, 2 could have, 3 could have, 4 could have, all 4 could have purchased a bow tie, but at least one of them did. Okay, so the probability of a bow tie is 0.03. That's given in the probability. The probability of the complement of that is 1 minus 0.03, or 0.97 would not be bow ties of the ties sold in the United States. And when you see this at least, many times a good strategy is to use the complement of the event. Okay, so the probability that you had 4 people and none of them chose a bow tie, okay, none of them, not any one, so that means you sold no bow ties, would be 0.97, 0.97, 0.97, 0.97, all multiplied together, it'd be 0.885. That of the 4 people, not one chose a bow tie, okay? The probability then of at least one would be 1 minus the probability of none, which is 0.115. Okay, that's tricky, and that's something that there'll probably be one problem on the test when you take it like that. So you have to watch out for that complementary event when you see the words at least. Okay. All right, that ends up with 4. So we're going to stop there, because this is tricky, and hopefully you have enough homework that you have some practice on this. Work on your homework, and we'll talk about and answer questions on Wednesday.